case, if I want to talk, I've got this search tree here as an example. And I'm interested in looking at the expected number of nodes in a successful search of a binary search tree. The outcome space, or the outcome space that I might be initially concerned with, is the value that I'm asked to look up. And so the outcome space in this case would be a query to look up 10, a query to look up 4, a 15, 2, etc. There's going to be both probabilities associated with each of those possible outcomes. And I've just made these values up. So suppose that looking up a 10 is a moderately probable thing that we might be asked to look up. The probability of looking up a 15 is less probable. And the probability of looking up a 17 farther down the line is most probable of these options. So I've just made this up. The values that we might associate in this case, that we are associating in this case with those different outcomes, is going to be the number of nodes that I have to visit. So if I'm asked to look up a 10, that's going to happen with probability 0.1, and that's going to require that I look up or I visit one node, the root. If I am asked to look up a 4, that's going to happen with probability 0.1, and that's going to require that I visit 2 nodes. Looking up a 15 with probability 0.05 will require I look at 2 nodes. And the example continues there. So if I want to compute the expected number of nodes, that is the expected value of this random variable number of nodes looked at, I would simply compute it as a sum of probabilities, the probability of each outcome times the cost or value of each outcome. And you see that there. Random variables are often used to represent cost or some other kind of utility value. At least that's the way that we'll often use them, even if I stop referring to them explicitly as random variables. I'm now looking at the slide that gives probabilistic games in the top right-hand corner. And you remember, hopefully before break, the lecture was on minimax search with alpha-beta pruning in competitive games. And there is a probabilistic variation on that. So if we want to do build a game player that plays Risk, in which, I don't know, if you've played, not played Risk, it involves taking over the simulated world. It's a board game, and you roll die to make decisions about the outcomes of, or evaluate the outcomes of decisions that are made by players. So here I've represented a probabilistic game tree, just in general. This is a very generic format for a game tree. But the top node, and I'm introducing a new convention here regarding representing nodes than I talked about last Tuesday in minimax search, regular minimax search. So we have a current player at the top, at the root, labeled by max node here, and the max node player has to make a judgment about where they're going to move or what decision they're going to make. Again, that could involve rolling a die, for example. There's a stochastic or a probabilistic aspect to this. So I'm playing Risk, and should I assault the army on the left and try and defeat them, or should I assault the army on the right and try and defeat them to take over their territory? It's unclear in Risk whether I'm going to succeed or not, regardless of how many soldiers or armies I've got at my disposal. And so there's also a representation here at the second level of what are called chance nodes. And each of the arcs from the max node to a chance node corresponds to an action that the max node player is evaluating and deciding whether they want to take or not. The chance node, here it says min rolls. So if max moves from down that left-hand branch, the min player is going to roll. If max were to decide to move down the right branch, the min player, his opponent or her opponent, would roll next. With some probability, if we're going now to the left child of the root, with some probability, the min player will come up with some result. And with some probability, the min node or min player will come up with another result. I've given those as 0.2 and 0.8 respectively. The min player then, represented by this downward pointing triangle, then is, depending what their role is going to make a decision. And those decisions could in turn lead the max player to roll and then make a decision based on that roll. And so down that leftmost path, you see that the max player would be taking a roll with 0.5 for one outcome and 0.5 for another. And so this is what a generic probabilistic games tree search would look like. At the very bottom here, in the very bottommost right or left corner, I've got the possible outcomes, which are board positions, B1 through Bn in this case. And I've got the values of those boards for the maximizing player. So B1 looks like a moderately good board. B6, a little farther down, looks like a exceptionally good board. B7, farther down, looks like I've dropped a link. It looks like a relatively poor board. And so going to the next slide, like regular minimax search, I'm going to be working from the bottom up. And again, this would probably be done in a depth-first search, even though I'm, or a depth-first enumeration of the possibilities, even though I'm showing this in a breadth-first manner. But the maximizing player would, down at the bottom level, would certainly prefer B1 to B2, would certainly prefer B4 to B3. And we get these maximizing values at the very bottom. But these maximizing values are only obtained, and I'm looking at the next slide now with the third level down filled out. These values of 5, 4, 8, 6 at the very bottommost level are only achieved with a certain probability each. And so the expected value of that next level up, you'll see a 4.5 is the expected value of the leftmost, bottommost chance node, because with 0.5 probability of 5 is obtained, with 0.5 probability of 4 is obtained. The next node over is a expected value of 8, because with probability 1, you're going to get a value of 8. But you can compute the expected probabilities, and I show the explicit computation here for the node with a 4.1 value in the center. These are the expected values of those nodes, and as you might guess, the minimizing player is going to choose the least of those expected values. So the minimizing player, the next level up, would choose 4.5 rather than 8, would choose 4.1 rather than 6. And you can follow that across. And then from that, we're going to generate in the node at the leftmost child, or the left child of the root, an expected value of 4.18 for that node, because that is the expected value given a probability of 0.2 times the value of 4.5 plus the probability of plus the product of a probability of 0.8 times the expected value of the previous or the rightmost child of 4.1. So in this case, the current player, Max, after computing these expected values, it's a virtual draw, almost arbitrary where they would choose, but the right child is the higher expected value. And so presumably that would be what the Max player would choose to do. Might do much worse than that if the chance knows, the die roll, the coin flips, whatever the source of uncertainty is, go the wrong way, but nonetheless, those are the expected values. Going to the next slide on conditional probability, we've talked about some of this with respect to the naive Bayesian classifier that we talked about 2 weeks ago in machine learning. A conditional probability is just a proportion of a joint probability of 2 or more events divided by the probability of the conditioning information, the information on the right-hand side of that vertical bar. So a couple of examples here. The probability of a flu given a sore throat is equal to the probability that a patient has the flu and is exhibiting a sore throat divided by the probability of a sore throat. The probability of a battery being dead given the car won't start is the joint probability of the dead battery and the car not starting divided by the probability of the car not starting. So this is often, conditional probabilities like this are used for prediction, just like they are in the Bayesian classifier we talked about. And that includes diagnosis, lots of diagnostic applications here. In terms of an objective probability assignment, which we also talked about, we can rewrite this conditional probability as a joint probability divided by a conditioning probability of the conditioning information. And this is going to be equal to we're going to re-express these various probabilities in terms of ratios. The probability of E1 and E2 is estimated to be the count of the number of instances that we have available that we've observed that show both E1 and E2 divided by the total number of observations that we've made in this domain. And this is divided by an estimate of the probability of E2, which is going to be the proportion E2 divided by the total number of objects. And so we can rewrite these conditional probabilities as proportions. We can use this additivity rule. Here are frequencies, not probabilities per se, but here I'm just defining the total number of observations as the total number of outcomes in instances in which both E1 and E2 are true, plus the total number of observations in which E1 and not E2 are true, and you can just continue with that. So that's the definition of a conditional probability. It's kind of critical that you have a good handle on that when we go forward. You certainly be expected to know about an exam too, so if there's some question about that, make sure that you come in. In general, a conditional expectation is, we can compute conditional expectations just like expected values. Here I've got a kind of very generic tree. And in this generic tree, I've asked you at the bottom of this slide to assume that you have a plan which is a system which is executing a plan, and the operators in this plan perhaps are scripts operators. You remember preconditions, but we're really concerned now with our effects of the operators. And rather than having certain effects, we might have a planner or a domain in which the effects of an operator of a strips operator are uncertain. They only, individual effect might only become true after the operator is applied with a certain probability. We hope high probability, but there's some probability, non-zero probability, that the effect might not be realized. And so we have various options here. But in this case, the conditional expectation of the effects that are true after executing particular operators, and the values associated with those expectations is given again by not a unconditioned probability times the utility, but a conditional probability times a utility. So the utilities of the individual states that we might associate or find at the very bottom of this search are given there. And we'd be interested in computing the expected utility that we obtained if we execute operator 1 in this particular example at the root, followed by operator 2. What would be the expected outcomes of executing operator 1 followed by operator 2 in a world in which the effects are uncertain? The next slide simply shows the computation. We would work from the bottom up, just like we did with probabilistic game tree search, and we would compute the expected values of the intermediate nodes, in this case S sub I 1 and S sub I 2, and then the root of the entire tree. And again, the intent there is to give the expected utility after executing op 1 and op 2 in a situation where the results are uncertain.